Hello, everyone. Good morning, good afternoon, and good evening. It's our great pleasure to have Professor Henry Curran today here to discuss progress in chemical kinetic mechanism development. So please allow me to introduce Professor Henry Curran briefly. Professor Curran received his PhD degree from the National University of Ireland, Galway in 1994. He worked as a postdoc researcher and research scientist in combustion modeling at the Lawrence Livermore National Lab, where with Dr. Charles Westbrook and Bill Pitz from 1994 to 1999. He was appointed lecturer at the National University of Ireland, Galway in 2005. He is currently director of the Combustion Chemistry Center, C3, I believe you know that, and the priority research area leader in energy at NUI Galway. He is a member of the editorial boards of Progress in Energy and Combustion Science and Combustion Theory and Modeling. He is a founder member of the Irish section of the Combustion Institute, a fellow of both the Institute of Chemistry of Ireland and the Royal Society of Chemistry. He became a member of the Royal Irish Academy in 2015. He was awarded the Boy Higgins Gold Medal in Chemistry by the Institute of Chemistry of Ireland in April 2017. He has been named by Climate Analytics, formerly Thomson Reuters, as among the top 1% of researchers cited in his field every year since 2014. If you ever conducted any numerical simulations on combustion, I believe you know these mechanisms. This definitely applies to me. Today, Professor Henry Curran will discuss the progress in chemical kinetic mechanism development. Let's welcome Professor Henry Curran.
Thank you very much, Wenting, and thanks for the kind words and the invitation to give this seminar. So today I want to give an update really on the progress that we've been making in the Computational Chemistry Consortium, which is technically it's a combined effort from my group at Galway in collaboration with Bill Pitz at Livermore, with Tiziano Faravelli and his group from the CREC group in Politechnico di Milano, and Heinz Pitsch and his group at RWTH Aachen University. And now we actually joining the consortium will be Stephen Klippenstein doing quantum chemistry calculations. Okay, so this is just a slide actually that I got a number of years ago. Brandon Rodavera actually was kind enough to give this slide to me. So it just shows the different types of fuels. So we have gasoline, diesel, and jet fuel, and the different types of fuels and the compositions of those. So for instance, gasoline has about 43% isoalkane and 10% N-alkanes with about 30% aromatics. And then diesel fuel, though, has less isoalkanes, about 35%, but a much higher fraction of N-alkanes, 30% as compared to 10%, with 23% aromatics. And then jet fuels is somewhat intermediate to those two different fuels. Okay, and if we look at the gas chromatograms of those fuels, you see that the hydrocarbons in petrol are centered around C8, ranging from C5 to C12. Diesel is centered around C16, ranging from C10 to C24. And then jet fuel is intermediate. It's centered around C12, ranging from C10 up to maybe C16. Okay, and so what we try to do as a community is to develop surrogate components which will represent the aromatic, isoalkane, and alkane, the major fuel components of those fuels, so that we can accurately predict not just the chemical properties, but also physical properties, such as viscosity and boiling point, hydrocarbon Sutting index, and so on. So, and in the C3 mechanism that we've developed through the consortium, we've developed mechanisms for the red structures that are provided in these pellets and as surrogate components for the different types of fuels. The orange components are actually largely components that are available mostly through Livermore, but also through ITV Aachen University and also Politecnico di Milano for different fuels. And this pellet in particular has been published very recently by Livermore. It was published in Combustion and Flame for diesel fuel. And I'll show you that citation a little bit later. Okay. So the idea of the Computational Chemistry Consortium, it's a collaborative effort where NUI Galway is largely responsible for the core chemistry. And I think most of you will be aware of the core chemistry that we've been working on now for the last 15 years or so. And so, but I've always maintained my collaboration with Livermore. And so they've continued to develop the large hydrocarbon mechanism chemistry. And so what we've been doing is developing the core chemistry at Galway and combining that with the large hydrocarbon chemistry at Livermore. And then Livermore also have some aromatic chemistry, but also Aachen and Milan have single and multi-component polyaromatic hydrocarbon chemistry, which is combined with the Galway Livermore chemistry into a larger C3 mechanism. Other components that are formed part of this mechanism are oxygenated species, including methanol, ethanol, and dimethyl ether. And also we have, as part of the consortium, NOx chemistry. So both Galway and Milan and some collaboration with Livermore also, we've been working on NOx hydrocarbon chemistry interactions. And I'll talk a little bit about that. Okay. So just to say then, years 1 and 2, what we've been doing, and this is just another synopsis of what I've just given. We've been working in Galway on this core C0 to C5, also working on methanol, ethanol, and DME. We've very recently just had a paper accepted on 1 and 2 pentene isomer structures, so that they can be components to represent the alkene component in gasoline surrogate mechanisms. We've also developed and optimized, based on the same rate rules and so on, 1-hexene mechanism formulation. And one thing I'd like to say, but I'm not going to talk about it here, is that, so there is, and I mentioned this in my talk in Dublin as well. So there is an interaction between alkane, alkene, and alcohol chemistry. And all of these are interlinked through the Waddington mechanism. And also, of course, so for alkanes, you get olefin plus HO2 from RO2 chemistry. And through the Waddington mechanism, when you've got an olefinic species, when OH hydroxy radical adds across the double bond, you get an alcohol radical. So all of these chemistries are interlinked, and what we want to do is have all of the mechanisms that are part, we'd say, so for instance, something like N-butane, butene, and butanol chemistry would all be interdependent, and so that we wouldn't have separate individual mechanisms for all of those 3 mechanisms, but have them all integrated. Okay, so that's what we've been working on. So we also then liaise, as I said before, with Livermore on the large mechanism development. And with the rate rules that we're using, we try to use similar rate rules across all of the alkanes, from small to larger ones. And we've been liaising with Milan on the NOx mechanism development. Livermore have been updating and constantly improving the n-Heptane isooctane toluene submechanisms. And as I show just very briefly later, they've developed a surrogate diesel fuel mechanism. Some of the components are listed here that are part of the C3 mechanism, but there's also lots of components that are not, that they've published. And also they've helped us with some of these smaller species like 1 and 2-heptene chemistry. As I said, Heinz and Tiziano, they're working on the polyaromatic mechanism to feed into submodeling, and they've also helped develop the N-dodecane chemistry. And one other thing I'm going to talk about is component library, because we'll see in a second that the mechanism that we've generated is very large, and how this isn't very practical for CFD applications. So what we want to do is to develop, or to be able to extract smaller mechanisms and then reduce those so that we can have mechanisms that can be practically used in CFD calculations. So Tiziano Faravelli and his group, working largely, the burden of the work is being performed by Raju, Mandhapati and Kuiwen Zhang at Convergent Science in using this component library approach. I'll talk about it a little bit later, to get to extract components from the large mechanism that we generated for all the species, and then perform a mechanism reduction. Okay, so in the first year of the Computational Chemistry Consortium, we developed mechanisms then and amalgamated them all. So we had the core chemistry, on which we then added the Livermore TPRF components, and these also included, the subchemistry included ethanol, 1,2-pentene, and we also then had an n-Heptane mechanism. And on top of that then, Milan and Aachen added their aromatic formation and NOx pollutant chemistry to that. And Milan and Convergent Science worked on the component library. From that, we developed C3 Mech version 1, which was published in September, or released in September 2019 to the industrial partners. This has 3,371 species and over 14,000 reactions. Okay, now this we hope to publish to the community and have it submitted to Combustion and Flame by the end of this year. Okay, so in year 2 then, one of the industrial partners wanted us to look at methanol diesel fuel interaction. So what we did was we looked at methanol and n-Heptane interaction. This paper has been accepted and I think is now online at Combustion and Flame. So Galway, we measured ignition delay times in both the shock tube and RCM, and at Aachen, the measured flame speed data for the pure fuels and also for mixtures, and I'll show that in a few minutes. We've been working on the component library. This should be actually Milan and mainly Convergent Science, so not Aachen, apologies. Okay, and we've been working towards developing then diesel surrogates and gasoline surrogates also. The components are all there, and CSI has the ability to generate reduced mechanisms for industrial partners so that they can be used in CFD calculations. And I'll be talking about the aromatic and NOx pollutant formation work that we've been doing in year 2 also. Okay, so we have released now to our partners a mechanism, C3 Mech version 2.1, in just last month in August, which has close to 4,000 species, 3,768 species and almost 16,000 reactions. So it's enormous, but it has core C0 to C5 chemistry developed at Galway. And I'll talk about a little bit later, we've updated as much as we can the core chemistry, but in particular, we focus on new high temperature, high pressure flame speed data that have become available in the literature. Okay, and I'll talk a little bit about that. As I said, we have published also, and it'll be available soon online, 1,2-pentene. It's been accepted to Combustion and Flame. And the 1-hexene paper, the mechanism is complete. The publication should be submitted in the next week or 2. We've been working on, so Kuiwen Zhang published a paper on the hexane isomers. So they have different molecular structures with different RON and MON values. And Livermore and Galway have been working on the rate rules and applying those to the hexane isomers, and then using those rate rules to refine the larger hydrocarbon chemistry, such as n-Heptane, isooctane, and the n-alkanes, n-octane up to n-dodecane. Okay, they've all been improved throughout the year. And of course, we're constantly trying to update the toluene and the larger aromatic hydrocarbon. In year 1, we had NOx chemistry with methane up to propane, but we've actually extended that now. So we have hydrocarbon NOx interaction chemistry from C0 to C7. And we have a publication there's one in review, I think, from Livermore on isooctane NOx interaction, and we're in Galway are currently preparing a publication on this. Okay, so why, I think most people on this call will understand why, but I just wanted to show this for non-experts that mightn't be, that might be also on the call. So if we take a large hydrocarbon like diisobutylene, which is an olefinic structure similar to isooctane, that can undergo H-atom abstraction to produce these daughter radicals, which undergo beta-scission reactions, producing isobutyl, isobutene, and here terbutyl and methylallyl radicals. Okay, so if we undergo unimolecular decomposition, we also generate isobutene, terbutyl, isobutyl radicals. Okay, so we can see that either via H-atom abstraction or unimolecular decomposition, diisobutylene very quickly becomes isobutene and isobutane chemistry. Okay, and we see this if we look at this plot here. We plotted isobutene and diisobutylene flame speed measurements as a function of equivalence ratio at similar conditions, and you can see that the isobutene and diisobutylene flame speeds, the experimental points here, are very similar. And so the chemistry of isobutene is influencing greatly the chemistry of diisobutylene in flames. Okay, so hence we want to develop and optimize the core chemistry. So what we've been looking at aldehyde chemistry, we've looked at adenine and propyne chemistry, as I said, we've looked at the NOx chemistry, we've looked at 1-hexene and 1-heptene. So let me just show you briefly some of the targets that we've looked at. So we've measured ignition delay times for 1-hexene. We've 3 equivalence ratios plotted here, 0.5, 1, and 2, at 2 different pressures, 15 and 30 bar. The points of the experimental results and the lines of the model predictions. And you can see that the model now, using the same rate rules that we have for 1 and 2 pentene, we have good agreement with 1-hexene here. And actually, I don't show it, but we've also good agreement using similar rate rules for 1-heptene also. Okay, so also data here, this is data from Frederic Baton Leclerc's group, where species profiles as a function of temperature are plotted, and again, the model captures the data quite well. And here we have 3 different sets of flame speed data taken recently, and again, we're over predicting the flame speed slightly, but there's pretty good agreement between the flames, the model and the experimental results. Okay. Okay, so looking at the effects of NOx addition on C1 to Cn alkanes, I give a couple of examples here. We have N-pentane with NO addition in a jet stirred reactor. And what we see actually is the baseline cases in both of these plots are the black symbols, okay? And so we see typical negative temperature coefficient reactivity for N-pentane. So no reaction up to about 550 Kelvin, then reactivity starts to increase. We get an increase here at between 625 and 650 Kelvin, a maximum increase in reactivity, and then the reactivity decreases in the negative temperature coefficient regime until there's virtually none, and then it increases again as we come out into the intermediate high temperature regime at around 800, 850 Kelvin, okay? If we add NO, just 500 ppm, and maybe 1000 ppm. So the blue symbols are adding 500 ppm, the red symbols adding 1000 ppm. What we see is a suppression of reactivity at lower temperature, but an increase in reactivity at high temperature. And the suppression is captured well by the model, although it's shifted to a little bit higher temperature for both the 500 and 1000 ppm addition. And also then we see the increase in reactivity at higher temperature. And this is captured by these experiments here taken in 2019, and these experiments by Zhao et al. At slightly different conditions published in 2018. I think, Yiguang, you were certainly part of one of these publications. I don't know which one, I'm sorry, but you're certainly part of it. But you can see again that we're over predicting the suppression reactivity at lower temperature, but we are capturing the increase in reactivity, and by and large the mechanism's capturing well the reactivity here. Okay. Also a similar story for n-Heptane with NO in a jet stirred reactor. Again, with 0 ppm NO, we see higher reactivity for the pure fuel on its own. We add 1000 ppm suppression reactivity at lower temperature and increased reactivity at high temperature, and that's captured well by the model. These data were published 14 years ago by Gladys Mariak, I think working with Fabian Maus. Okay, so just another area that we've been working is on laminar burning velocities. I don't want to go into it. This is pretty well known, and it's sort of standard validation data. So we have data here taken at 3 and 5 atmospheres up to 20 atmospheres. I think most of these data would have been taken by Ed Law and students working with Ed over the years. But I also then just want to show here we have data for methane, methanol, ethane, ethanol, ethylene, acetaldehyde, acetylene, propane. There's allene and propane here. And you can see for all of these plots, the lines capture the data well, okay, across a wide range of conditions, both as a function of equivalence ratio, temperature, and pressure. Okay, so one thing and this is all in one mechanism, which is almost 4,000 species. So here's just some, of course, the primary reference fields are important. So we've looked at n-Heptane as, here we have flame speed as a function of equivalence ratio at different temperatures. And here's some more data. It's well captured by the model. But just to show them, these are more recent data taken by Ron Hansen's group in the shock tube at Stanford, where they're measuring now flame speeds at higher temperatures than were measured before. And you can see here for n-Heptane, again, we're capturing the data well. Okay, and these are some more recent data at higher, just higher pressure data. Okay, so then as part of the work with the consortium, they were interested in these n-Heptane methanol interaction chemistry I was talking about a little earlier. So here's a couple of slides where we've taken new data at different pressures, and again, the data is well captured. But this plot is interesting, where we show the influence of mixture composition. So if we look at an equivalence ratio at 1.2 here, and we add, we'd say 20, 50, and then 100% ethanol to n-Heptane, we see an increase in flame speed measured at 1 atmosphere and 2.5 atmosphere. And the line here is the model prediction of the influence on flame speed of methanol addition. You can see that it's well captured, the points of the experimental results. Okay, and these data were taken actually, Shamai Bariki and Joaquin Beekman. So these are part of a publication that we've submitted for review in Combustion and Flame currently. Okay, just to stay on the flame speed theme, I should have shown, and I'm sorry I haven't got them here. I should have shown we also have ignition delay time measurements. The ignition delay time measurements are very well predicted by the model. And so we get much less reactivity if we add methanol to n-Heptane. Okay. Also, we have flame speed predictions here. And the idea is to try and validate the model beyond the range of traditional flame speed data, which I've shown you, to much higher temperatures and pressures than we've seen before. And so these are recent data published last year by Alison Ferris, working with Ron Hansen at Stanford, where she measured flame speed for methane, ethane, and propane at 1 atmosphere, but at higher temperature conditions in the shock tube than would have been reported previously. And you can see, except for ethane, we're under predicting by about 10%. We're capturing well the data for methane, where we're slightly under here for the Stanford data, but these previous data were a little bit faster. So But for propane here, we're capturing the data certainly within the error bars pretty well. Okay, and then these are new data just published recently by Foki Ngafopoulos and his group, just from this year, at room temperature, but at higher pressures than published previously. So these are for methane and these are for ethane. So here the points, sorry, these are points with error bars, and the red line is the model prediction of these high pressure. So these data range from about 7 to 15 bar, but then these other data extend that range up to 30 bar. And you can see that the model is capturing the data quite well. We're a little bit too fast here for ethane as we go to higher pressure. Okay, but for propane and propene, again, the model is predicting that data quite well. Okay, so if okay, so I'll just move on. I just want to talk about a little bit about the status of the detailed kinetic mechanism for diesel surrogates and the large hydrocarbon mechanism developed at Livermore. And these are the main participants in that: Gautam Kukadapu, Kuiwen Zhang, Scott Wagnon, Bill Pitz, and Marco Mel. Marco has moved back to Politechnico di Milano, and Kuiwen is now working at Convergent Science. Okay, so in year 2, as part of the project, as I said, Livermore used and updated the rate rules for the hexane isomers. So here's some of the branched 2,4-dimethyl butane, 2-methylpentane, and 3-methylpentane to help validate the large isoalkanes, including isooctane in C3 Mech version 2.1. We've also they've also developed mechanisms for NC9 up through n-Dodecane, C12, and helped with the development of some of the smaller species chemistry that I've shown a little bit earlier. Okay, so this is just current model prediction versus experimental data for n-octane, n-nonane, n-decane, and n-dodecane. And these data are published in, this is the surrogate diesel fuel mechanism that I referred to a little bit earlier from Livermore. Here's the citation for it. But you can see here that the data at 21 bar for n-octane as a function of equivalence ratio is captured pretty well by the model. It's a little bit under-predicted here at stoichiometric and rich conditions at low temperature, and a little bit under-predicted here at high temperature. In the NTC behavior is well captured by the mechanism. Here for n-nonane, again, the agreement is pretty good. And here for n-decane, the pressure effect on reactivity is well captured by the model, ranging from 13.5 atmospheres up to 80 atmospheres. And again, for n-dodecane, up to high pressures. In talking with Bill Pitz at Livermore, they suspect that the data here at high pressures, 60 and 80 bar, may be suspect, and we may want to, within the community, repeat some of these data just to check that these are in fact correct. There's some disagreement between the model predictions and the experiment here. Okay, as I said, using the hexane isomers, Livermore have also been updating the rate rules for the branched alkanes. Here's the hexane isomer predictions, the points of the experimental results and the lines of the model predictions. And again, they're in pretty good agreement. But they've also now applied those rate rules then to the isooctane, isododecane, isocetane, and use that in the diesel submodel or diesel fuel surrogate modeling. And again, here's the citation for that. Okay, and here's some then 4, 5, and 8 components fuel. The RCM experiments were taken at the University of Connecticut. These are again published in this paper. You can look at this publication yourselves, but you can see that the model is capturing the reactivity of these different surrogate component mixtures quite well. And they do have different reactivities, and the reactivities, okay, not hugely accurately captured here at high temperatures, but the overall trends certainly qualitatively are well predicted, although quantitatively could be improved. Okay, so to move on to the polyaromatic hydrocarbon mechanism development, this is performed by Heinz Pitsch's group and also Tiziano Faravelli's group, a collaborative effort between them in developing the aromatic hydrocarbon chemistry. So again, just to go back to this component concept of how the model is being developed, NUI Galway is responsible here for the core chemistry. Livermore is responsible for the large hydrocarbon chemistry, and then Politechnico di Milano and Aachen are responsible largely for the aromatic and polyaromatic hydrocarbon chemistry. So there's some overlap and some areas where we have to decide where we take the mechanisms from. For instance, even though the core chemistry, and when I say core chemistry, we have C5 up, like at least up to C-pentane and pentenes and 1,3-pentadiene chemistry in there, but also then there's cyclopentadiene and cyclopentane chemistry, but that overlaps with the polyaromatic hydrocarbon chemistry. So so that we can have easy combination of the chemistry and good predictions of aromatic and polyaromatic hydrocarbon chemistry, the cyclopentadiene chemistry is actually taken from that developed at Aachen. Okay, and also the 1 and 2 ring aromatic hydrocarbon chemistry is taken from the Aachen group. The toluene and phenol chemistry and the C2 to C4 aromatic hydrocarbon chemistry is taken from the Polimi group, and the larger hydrocarbons, as I said before, are taken from Livermore. And this is a shaded area. We do have some NOx chemistry included. So here I'm just showing a synopsis here of 2-ring polyaromatic hydrocarbon predictions in different reactors. So here we're looking at parity diagrams. So here we have simulation plotted on the y-axis versus experimental mole fractions on the x-axis for different components. So here we have indene and naphthalene measured in jet stirred reactors, perfectly stirred reactors, and shot tubes. Those two species measured in counterflow flames and measured in premixed flames. And each point here is an experimental target. So there's about 20 different experimental targets. And you can see the previous version of the C3 mechanism is these open square symbols, and the current version, C3 Mech version 2.1, are these triangles. And you can see that the triangles are coming much more onto the center line, and it's showing the improved accuracy of the chemistry that's included in the mechanism for the prediction of these species, which are important to prediction of ultimately of subformation in flames, or in the oxidation of any hydrocarbons. Okay. Here's just some further examples. Here's cyclopentadiene oxidation in a jet stirred reactor. These were published just recently in 2020. Again, the red lines here are the current model predictions. The blue lines are previous mechanism predictions. And you can see for most species, certainly for the cyclopentadiene, the fuel, and some of the major O2, CO, CO2, and hydrogen, the predictions are much more accurate now with this combined effort model. The core Galway chemistry, the large hydrocarbon chemistry from Livermore, and the aromatic chemistry from Aachen and Milan. Okay, and for most species, the predictions are improved. And a lot of the focus this year in the aromatic chemistry development has been on cyclopentadiene and cyclopentadienyl radical chemistry, generating indene and naphthalene in particular, but also other species. Okay, so here's another flame. It's not as well predicted, I would say, or sorry, another experimental result. It's actually, again, not a flame, it's just sort of reactor data for benzene oxidation. This is from Lisa Pefferly back in 1998. you can see, again, the reactivity is underpredicted by the model, but it's a little bit improved over previous predictions, and a lot of these intermediate species are better predicted now than they were before. And again, it comes down to the focus that's been paid to the cyclopentadienyl chemistry in generating these species. Okay, another, this is a toluene ethylene flame. We've got, I think, 2 of them depicted here. Sorry, this is the fuel, and we have oxidizer. Sorry, this is an post-flow flame, and we're seeing the fuel, the 2 different fuels. I think this is ethylene, and this is toluene. And you, again, the red lines are the current model predictions. The blue lines are the previous model predictions. In general, the red lines are in better agreement than the blue lines, and it's just showing the improvements of the mechanism across the different experimental data available in the literature. Okay, and this is one last flame. This is for a toluene premix flame. Again, there's a wide range of experimental targets available, but there's one here at 5.1. This is data taken from 2011. And again, you can see the good agreement of the model against most of these species. And again, some improvement overall against the target data. Some improvement in naphthalene is coming down a little bit. Okay, so we're not only, of course, we have to predict the formation of aromatic species and in the oxidation of these species, but also we also have to predict ignition delay times. So here's benzene ignition, and you can see here this is the previous predictions in blue and the current predictions in red. And again, the agreement is excellent across the range of conditions presented here for the data taken from this publication. Okay, here's other data taken for toluene, and again, there's very good agreement between the experimental results, which are the points, and model predictions, which are the lines. Okay. Okay. Finally, so we have this very large mechanism, and as I said, it's like almost 4,000 species and 16,000 reactions. So how do we manage to generate mechanisms from that can be used in practical applications and practical modeling studies? Okay, so Raju, Mandhapati, and Kuiwen Zhang at Convergent Science, with some input from Tiziano Faravelli's group at Politechnico di Milano, have been working on this. Okay, so what we've decided to do is to take a top-down approach rather than a bottom-up. So we want to start with the detailed mechanism. So we're starting with everything. You know, we put in the kitchen sink into the mechanism, everything's included. And then what we want to do is extract the necessary species and reactions from for the fuel components of interest and at the operating conditions of interest. And then thereafter perform a 2-step reduction procedure. Based on the fuel components of interest, extract the relevant sub-mechanism. So we get just the fuel components that we want in the first step. And the second step then is to perform a directed relation graph with error propagation reduction, starting with the sub-mechanism to obtain a smaller skeletal mechanism that can be used in CFD simulations. Okay, so here's the step 1, extracting the sub-mechanism. So we have all these fuel components. We could have, I don't know, maybe 20 or 30 different fuel components present in the mechanism. And each fuel component has a species list associated with it. So it's not easy to extract and generate a sub-mechanism based on this huge, like 4,000 species mechanism. But if we provide a list, so and I'll show you in a second, but if we have a fuel component like n-Heptane, for instance, n-Heptane we will provide, and when I say that the technical partners responsible, so Go and Livermore will provide Convergent Science with the species list that's necessary to simulate accurately n-Heptane oxidation. And then, so that species is provided. So if you want n-Heptane, isooctane, and toluene as your gasoline surrogate, each of those three components will have a species list. That species list then will be combined into a unified species list. And then there's an extraction tool that has been developed by Convergent Science. They'll take the large mechanism, use the extraction tool, in conjunction with this unified species list to generate the sub-mechanism for n-Heptane, isooctane, and toluene. Okay, and so we have, these are just some of the species, and I'll show you a list later, but we have all these core species. So we've hydrogen, we've got CO, we can do syngas, we've got methane, ethane, ethylene, acetylene, propane, propene, propyne, alene, butane, butene, 1-butene, 2-butene, 1,3-butadiene, isobutene, isobutane. All of these components are all part of the core mechanism. Acetaldehyde, formaldehyde, methanol, ethanol, dimethyl ether. Okay, and so all of those core species will have a species list associated with them so that we can accurately simulate that particular species. And then you can, if you want to do fuel flexibility studies where you want to take, for example, methanol with N-dodecane as a surrogate diesel fuel, you can just extract the sub-mechanisms for those two species, generate a sub-mechanism, and then from that use DGR-EP to generate a reduced mechanism. Okay, so that's what I'm showing here. So we started here with a C3 Mech version 1 with 3,374 species, and then with the species list for n-Heptane, and again this is a detailed n-Heptane mechanism, we can extract within a few seconds the sub-mechanism for n-Heptane, and that contains 1,053 species. And then here's just 9 different conditions. So we have 5, 10, and 15 bar pressure at 5.6.5, 1, and 1.3. And these are ignition delay time predictions using the detailed mechanism, the extracted mechanism. You can see that they lie on top of one another. You can't see any difference in the predictions of the two mechanisms. So you can see that the extracted mechanism is as accurate as the detailed mechanism. But of course, that sub-mechanism is 1/3 the size and is going to be much, much faster in simulating the performance simulations than the detailed one. Okay. So step 2 then is we take the mechanism reduction tool in Convergent Science edition 1, which uses DGR-EP to take the extracted sub-mechanism, reduce it further, and to generate a reduced skeletal mechanism. Okay, and also, of course, we have to take the operating conditions of interest. So that to generate reduced skeletal mechanisms, we can generate them. For instance, if we want to simulate oxidation, just high temperature oxidation. If we want to do auto ignition, so if we want the low temperature chemistry included, or do we want polyaromatic hydrocarbon, and for ultimately sub predictions, what chemistry is needed for that. So we need the operating conditions of interest, the temperature range, pressure range, and then the appropriate sub-mechanism so that we can generate a useful reduced skeleton mechanism that can be used in CFD. Okay. So this is the range of fuels validated in C3 Mech version 2.1 for alkanes. You can see we have all the alkanes up to n-Heptane, including the hexane isomers. I haven't included them all here in the list. Over a wide range of temperature, pressure, and equivalence ratio conditions for a wide range of reactors. Some, like methane, has them all. Methane, the smaller species, has them all, where we have a wide range of data available in the literature. But sometimes for other fuels, we don't have as wide a range of data. And so we take it where we can get it to validate the mechanism. Okay. We also then, for larger hydrocarbons, of course, isooctane is a primary reference fuel. We have the N-alkanes from N-octane to N-dodecane. We have isododecane and transdecylene also included, and we have chemistry for toluene, benzene. They're not alkanes, of course, they're aromatics. But also we have N-alkane chemistry now plus NOx interaction. We've taken in Galway unpublished data for shock tube and RCM ignition delay times with and without NOx, which we will be publishing in the near future. And again, over a wide range of conditions of temperature, pressure, and equivalence ratio. Okay. We also have taken a wide range of data, you know, in the core chemistry for alkene chemistry. The most recent that I showed some examples. We've 1 and 2 pentene published. We've developed data our mechanisms now for 1-hexene and also actually for 1-heptane also. Again, over a wide range of temperature, pressure, and equivalence ratio. And also then for oxygenated and we'd say hydrogen and syngas chemistry, and also aldehyde chemistry. I haven't gone into it, but we have accurate chemistry now for formaldehyde, acetaldehyde, propanal, and butanal, and also pentanal most recently. And this is interesting. I'm not going to talk about it here, but in recent modeling on cyclopentane, we find that there's a ring opening reaction in the low temperature chemistry, which forms an aldehyde radical, which is a radical from pentanal. And that chemistry is important in the accurate prediction of ignition delay times for cyclopentane chemistry. So actually accurate aldehyde chemistry is important, particularly at lower temperatures, because we're getting high concentrations of these aldehydes formed at low temperatures. And so to have accurate sub-mechanisms for these species is actually important in accurate predictions of the large hydrocarbons and ring paraffins. Okay. We've also then alcohol, and we had a particular attention focus on methanol and n-Heptane mixtures. We've ethanol and propanol and isopropanol in the mechanism, and dimethyl ether also. And then these are just showing polyaromatic validation database. So I didn't mention it, but there's about 102 different target data sets that Milan and Aachen are using to validate the polyaromatic hydrocarbon chemistry against. And these are they're using premixed and counterflow flames, jet stirred reactor and flow reactor data, shock tube and RCM data for different species. And so these are the different fuels that they're validating the aromatic chemistry against. And this is the temperature, temperature, pressure, and equivalence ratio range. Sometimes they're under pyrolysis conditions, hence the infinity here. And so I just gave you a flavor in my presentation of the kind of predictions that we're getting with this mechanism. But this mechanism is one mechanism that has at its core, the hydrogen oxygen chemistry all the way up to this aromatic phenol, indene, naphthalene, and also A3 and A4 species also, okay, as part of it, okay? So this is the work that we've done. I think I've shown you this already. One thing we haven't done is looked at gasoline and diesel surrogates. Well, Livermore have published a diesel surrogate mechanism, but in year 3, one thing we're going to be doing is looking at some gasolines, taking experimental results for ignition delay and flame speeds for certain gasolines. One was Euro 95 gasoline, another will be US 87, and a third one will be typical China gasoline that will take experimental results and possibly have a surrogate mechanism to simulate those real fuels. Okay, these are then just a list of some publications that have stemmed from this. And one I would point to in particular is this number 1. So this is a paper that was led by Matteo, but it includes all the technical partners so far. As I said, Stephen Klippenstein is joining in year 3. But this really discusses C3 Mech version 1, and it gives a good overview of the philosophy that I've just shared with you on the mechanism formulation. And the mechanism, I think C3 Mech version 1.0 is available through that. And if you're looking for it, we can provide that to you, okay, in the near future. Certainly, the publication, as I said, will be coming out toward, we'll be submitting it towards the end of the year. Okay, so that should be available soon. Okay, other publications are either in press or under review. There's a list of them here, and you can see this list and hopefully be able to either download them. Most of them, if they're in press or accepted, they'll probably be available online very, very soon. Okay, so this is the full list. We have about 11 publications already from the project. Okay, there's one thing, if I can, I'll try and open another presentation where I show ignition delay targets for the methanol and heptane mixtures. Yeah, so that's just the methanol and heptane blend. So what we've taken a lot of data actually for these blends. So we've plotted here 3 different pressures. So A is 10 bar, 20 bar, 30 bar. And you see here, we have 100% methanol all the way up to 100% n-Heptane. And here we have a 50-50 mixture, a 75 n-Heptane, 25% methanol mixture. And again, the points are the experimental results and the lines of the model predictions. And you can see the lines are capturing the data very well. Okay, the model is predicting the antagonistic effect of methanol on n-Heptane very well. Okay, one thing you see that it actually is antagonistic at low temperature, but if we go to higher temperature conditions, actually methanol is actually faster to ignite compared to n-Heptane. Okay, and that's just due to, you know, we get a lot of formaldehyde, formal and fast reaction, formal radical chemistry from methanol at high temperature, which we don't get as much from n-Heptane. Okay, so you can see here over the range of pressures, it's well captured, and then we see here again the effective equivalence ratio for 50-50 mixture. Okay, where it's been well predicted by the model. Okay, so I just wanted to show that. I should have included that slide in the other presentation. So again, this is all part of the work that we've been doing. Okay, so thanks everybody for logging in and listening. And if you have any questions, I'll be happy to answer them.
Okay, thank you very much, Henry. So I received a few questions. So I will ask directly on their behalf.
Okay,
so the
sure.
first question is from Professor Zhang. Are lean blowout, ignition, and extinction limits still the challenges to address first before addressing soot and other pollutants?
I agree. It's more of a challenge, and it's something that we haven't focused a lot on in Galway. I'd like to check it. I know there are some data sets available. Some none come to mind right now, but it's certainly a good point, and it's something that we should look at. But from what I've seen, we do try and validate the mechanism to as over a wide range of condition as we can, for as many targets as we can. Okay.
Okay. Thank you. A second question is from Professor Yiguang. Do you have a plan to add ozone chemistry into your mechanism for unsaturated hydrocarbons?
It's not a specific plan, but it's something that we could do, I'm sure. But we don't have a specific plan to do that in the near future. But certainly, if there's interest in it, and if Yiguang is interested, we could certainly try it out and work with him on it, if that would be of interest to him.
Okay, great. The following question is from Professor Coles. With hydrogen and potentially methane and ammonia gaining importance, is everything solved? for hydrogen mixture and small hydrocarbon containing molecules?
I wouldn't say everything is solved. I think, you know, one thing I mentioned was we're asking Stephen, and maybe I could share this slide with everybody as well, if I will be allowed. So I've asked Stephen Klippenstein to come on board for next year. Okay, so one thing, yeah, let me just see, can I open it? Year 3. So one thing that Stephen's doing. So here's the plan for Stephen to work on in year 3. Let me just share this. So this is something, so, and this is something I'm quite happy to get feedback on this, but one thing that industry is concerned about, that the thermal NOx rate constant may not be right. Some people feel that it may be a little bit fast by about 20% or so. And so the first thing I've asked Stephen to do is to do a very high level calculation on the N2+O reaction, okay? But also then there's a list of important reactions here that are important for prompt NOx, the prompt NOx mechanism. So the CH and CH2 chemistry is very important there. And these stem primarily from work that Jeff Berg-Thurston did in collaboration with Siemens in Canada. And this came out of ASME work that we had been collaborating with them at the time, but they published this on the prompt NOx. And the rate constants, I think, are not very accurate for these small species, and they need to be if we want to get accurate predictions of prompt NOx. Okay, so I think that's going to be a big improvement for the community, calculating this.
Could just follow up, because I have a background for this question. We've recently looked at the interactions of things like DME, DMM, methane, and so on with NO and ammonia in some regions of, you know, intermediate temperature. And we're really puzzled how little development there has been into these systems.
Yeah.
And so, you know, there seems to be activity not only at the high end of molecular components that is needed, but also for the small hydrogen-rich systems. Thanks.
Yeah, thanks. I agree with you, Katharina. And I think, like, understanding how the RO2-NO, that, you know, the RO2 chemistry and NO2 chemistry interact is important. Agree very much with you there. We haven't, one thing we haven't included actually in C3 Mech yet is an ammonia mechanism.
Okay, thank you very much. So I will take a privilege to ask a question from myself. And our recent work on methane hydrogen CO mixtures at high pressure, even though we go to a high of 200 bar or even higher, and in argon diluent and CO2 diluent, and we found Aramco Mach 2 2.0 works very well. So as experimentalist, it's kind of disappointing because everything agrees well with modeling. But the good news for science. So what I want to ask is, do you have any recommendations for what we should target in the future at high pressure conditions, or does high pressure really matters?
Well, I think high pressure does really matter, okay? And this is no offense. I don't mean, okay, so I think it is like, so practical combustors work, and they will work more and more at high pressure. So like high pressures do matter a lot, and having fundamental experiments where we can validate the mechanisms at those conditions is really excellent. So I think I would encourage people, you know, to, and just because you got data and the model captured it, I wouldn't be disappointed. It's nice to know that the model is capturing it, but it's still valuable validation that the mechanism is accurate in that regime. And that, you know, if you want to go to EGR condition, for instance, it is reassuring to note that your results validate the predictions under those conditions. So, and the more data that we can get at higher pressures, the better, I would say.
Okay, thank you very much for the comment. And the following, the following question is from Soyang from University of Minnesota. To what extent have the high pressure and transcritical supercritical effects been taken into account in the mechanism, or any future plan on that?
Well, we have I suppose the small species chemistry have a lot of pressure dependent rate constants in there. We've included p-logs for a lot of those small species chemistry, which make a difference in predicting the pressure effect. You can see from some of the data that I showed you for the larger hydrocarbons, we're capturing that pressure effect well. The supercritical chemistry, I'm not so sure about, and I think that's probably an area where the community as a whole probably could do with more effort on the supercritical side, because I don't know, like, what about other species chemistry that might be important under supercritical conditions. So I'm not that familiar with it, but I'm sure there's work to be done there. I wouldn't take it for granted that we could go seamlessly to supercritical conditions.
I see. Okay, thank you very much. The next question is from Professor Porani. What is your most puzzling unresolved problem? If you could ask God one question about combustion chemistry, what would that question be?
Oh, I don't know. I don't know if I can answer that. Is there one rate constant that, I suppose, like when I talk to my undergraduate students, you know, I say kineticist is a rate constant determiner. Okay, that's really our job. So, like, for me, if we can get accurate rate constants, so if I could know everything within 5% and have a rate constant that's accurate over a wide range of temperature and pressure within 5%, I'd be happy. I don't know whether that answers the question.
Okay, thank you very much. That's definitely a challenging question. Okay. The next question is from Niels. How do you ensure consistency between the different parts of the mechanism from the different labs with respect to, for example, thermal and transport data?
Yeah, it's really difficult, Niels. It's really so I would say, like, so for instance, the thermochemistry, I would say, is not consistent throughout. That might be startling to people, but, like, for instance, we take, I think a lot of the core thermochemistry will be taken for the small species chemistry, are taken from as accurate as we can from the Branko-Rucich's active thermochemical tables where we can. But unfortunately, that's only really accurate for heats of formation. But we take the most accurate we can for the small species chemistry. As we go up, we try and take, so where we'd say Stephen Klippenstein, Larry Harding, Franklin Goldsmith would have calculated thermochemistry for the smaller RO2 QOH chemistry, we take it from there. But for the larger hydrocarbon chemistry, we can just try and extrapolate what we know from those up to higher ones and use therm to estimate it. Okay, so that's where I would say it's inconsistent. We actually have a project with Stephen Klippenstein, who's done high-level calculations on low temperature RO2 QOH species, where we can estimate or calculate within, I would say, for alkanes and alkyl radicals, a half kilocalorie per mole of the ab initio calculation up to C8, C9 species. So that's really nice. Okay, and we're getting, we'd say, about 1.5 to 2 kilocalorie per mole difference in heats of formation for C8, C9 species, but for the RO2 and QAH species. But we're continuing to work on that, and hopefully, again, we'll be publishing that towards the end of the year. And I think that will be a major step forward, working with Stephen on getting consistent low temperature oxygenated species. So the RO2 QOHs, O2 QAHs, ketohydroperoxide, getting much more accurate thermochemistry of those species will lead to increased accuracy of the low temperature predictions of mechanisms. But we're still in the realm where, like, 1 or 2 kilocalories per mole at 600 Kelvin is it makes a huge influence on predictions. And that's an area where the community at large still needs to do a lot of work, I would say.
Thank you.
Consistency, it's a big long-winded answer, and maybe it's not.
No, thank you. That was really helpful. Thank you.
Yeah.
Okay, thank you very much. The last question I could ask today is, will the mechanism be available on fieldmech.org?
It will be. And so as soon as we, I think as soon as we've submitted the paper for publication, we'll make it available to the community. Okay, so C3 Mech version 1 will be made available. So what we plan to do is, currently C3 Mech version 2.1 just last month was made available to the industrial partners. So what we want to do is maybe, you know, give them an advantage because they're funding the effort. So they should get, you know, an advantage of seeing the work, the model first, but that we would share with the community the previous model once the current model is available. So we'll be maybe a little bit behind in providing to the community the most up-to-date model, but certainly C3 Mech version 1 will be available very soon to the community. But what I like about it is that it is a one-stop shop where you have all these different components all in one place. And if you want to do fuel flexibility studies, you should get accurate predictions with that one mechanism. And so what you're not doing is taking a methanol mechanism from this publication and an n-Heptane mechanism from this other publication, trying to put them together and combining that and having an accurate prediction of methanol and n-Heptane mixtures. That probably won't work. In most cases it doesn't, but in this case it should. And that was the whole idea, and that's the concept of C3 Mech. Okay.
Okay, thank you very much, Professor Henry Curran. Because the limitation of time, and I won't be able to ask more questions. So
Okay.
it's really a great opportunity to have you present it for us and to communicate with you. Okay, thank you very much. One more time.
Thank you. Thank you for the invitation. It was a pleasure.